So far in this lecture, we've talked extensively about the first isomorphism theorem for rings. But when we talked about groups, there were 4 isomorphism theorems. So in this last video, I want to talk briefly about the other isomorphism theorems for rings. So let's say R is a ring. The first statement I want to talk about is the second isomorphism theorem for rings. Remember, this is the one that's the diamond isomorphism theorem because you draw this diagram that looks like a diamond. Let's say A is a subring of R and B is an ideal of R. We're going to define this set A plus B to be the set of all things that are something in A plus something in B. And the isomorphism theorem says, 1, this is a subring of R. 2, A intersect B is an ideal of R. And 3, just like for groups, it says that 2 quotients are isomorphic to each other. Here, it's the quotient A plus B mod B is isomorphic to A modulo A intersect B. So I'll say something about the proof later, and I'll come back to this also at in a minute. The third isomorphism theorem for rings, this is the take quotients and cancel like you would with fractions one, says, okay, let's let I and J be 2 ideals of R where I is contained in J. Then J modulo I is an ideal of R modulo I, and the quotient R mod I modulo J mod I, so the quotient by an ideal is a ring. What ring is it? Well, it's isomorphic to R mod J. So here, Dummit and Foote give a little proof sketch, and I'll actually give a little more information than what they say. They say that the map giving the isomorphism here is given by phi goes from R mod I to R mod J, and it's defined by, well, you have to say, where do you send the coset of I containing R? You send it to the coset of J containing a little r. And what do we need then for this theorem, this part of the theorem to hold, is we want to apply the first isomorphism theorem where if this map is surjective and the kernel is the ideal J modulo I, then we'll be done. Okay, so we first have to check that this actually is a ring homomorphism. And to see that it's a group homomorphism, well, it's just like what we did when we did the proof of the third isomorphism theorem for groups, except that it's a little easier because all the groups that are involved are abelian. So you also have to check that this function behaves well with respect to multiplication. And that's just an exercise in like writing down what this function does. So phi of R plus I times S plus I, the definition of the product in this ring, R mod I, says that that is phi of RS plus I. By the definition of phi, this is RS plus J, which is R plus J times S plus J, by the definition of multiplication in R mod J. And that just is phi of R plus I times R plus J. So I'm not giving a fully detailed proof here, but this is the big idea. Okay, so we'll move on and talk about the fourth isomorphism theorem for rings. But before I do, let me say that, okay, so this is how these theorems are presented in Dummit and Foote. But how do the statements change if you use these other definitions for rings? Say you insist that a ring must have a 1 and a subring must also contain that multiplicative identity of the ring, and a ring homomorphism must take the identity of the first ring to the identity of the second ring. Well, how do these statements change? This first statement does not change at all. The statement is exactly the same, except now R is a ring with an identity, A is a subring, meaning A also contains that identity, and this isomorphism here, the function that you show is a ring homomorphism in the like Dummit and Foote sort of standard setting, you have to add one more sentence about what it does to the multiplicative identities of these 2 rings. So the statement doesn't change at all. The proof, you have to add just a comment about what happens with the identities. Third isomorphism theorem, how do things change when you have these other definitions in mind? Well, R now is a ring with identity. But other than that, the statement is exactly the same. So this is a case where, in a way, the statement as presented in Dummit and Foote is actually a little bit stronger, because now it's telling you something about subrings and ideals of rings that don't necessarily contain an identity. And also, even if R does contain an identity, so this is telling you something that's true about subrings that don't necessarily contain the identity of the ring R. But they're so close to being the same thing. So what I'm trying to convey is that whatever definition you decide to take with you in your life after the end of this class, these statements should not be confusing. You can just remember like exactly what these say. And if you decide that your rings must have a 1 and your subrings must contain that identity, and your ring homomorphisms must send the identity to the identity, all you have to do is add sort of one small comment at the end. Okay, so I'm going to pause and erase and then say something about the fourth isomorphism theorem for rings, and then say more about the proofs that I'm leaving out, say at least a little bit. Let's now turn to the fourth isomorphism theorem for rings, or lattice isomorphism theorem for rings. Let's say I is an ideal of R. There's a correspondence that goes between A and A mod I that is an inclusion-preserving bijection between, on the first hand, the set of subrings of R that contain this ideal I, and on the other hand, the set of subrings of R mod I. Furthermore, this correspondence preserves the property of being an ideal. So A, on this side, one of these subrings that contains I, has the additional structure of being an ideal of R if and only if A mod I, this subring of R mod I on the other side, has the property of being an ideal of R mod I. Okay, so how does this work if you have these other ideas about definitions about like what it means to be a subring? So in the references that I have seen recently with Conrad's definitions for rings, I have just seen the second part here, that if you have an ideal of R that contains I, this has this inclusion preserving bijection between the set of ideals of R that contain I and the set of ideals of R mod I. So this is another case where really Dummit and Foote's definition is giving a little bit more, because it's telling you something about this correspondence between these additive subgroups that are closed under multiplication, but are not necessarily ideals in your ring, which is a stronger condition. Okay, but the main thing to remember is the same as like the big part of this lattice isomorphism theorem for groups, which is just that there's this correspondence between subgroups that contain your normal subgroup n and subgroups of G modulo n. So it goes the same way. All right, so I just want to say a little bit about the proofs. How do the proofs work? They work just like they work for the isomorphism theorems for groups, except in a lot of ways they're a little bit easier, because one of the tricky things for the isomorphism theorems for groups is you have to show that there are these isomorphisms between groups, and some of those groups are quotients. So you need to show that the thing that you're quotienting by really is a normal subgroup and not just like any subgroup. So for rings, since the underlying groups are abelian, that part you sort of get for free. And the price that you have to pay is that you must also check that whatever isomorphisms you're writing down in these statements behave well with respect to multiplication. So you have to check some statements of the form phi of xy equals phi of x times phi of y. Okay, so I'll leave an exercise to you to prove all of these statements. But really what I'm going to do is, you should think about it. It's a useful exercise, but I'll put up some additional notes, two different sets of notes one that proves the isomorphism theorems for rings in full as stated in Dummit and Foote, and another one that proves the corresponding statements when you have these additional definitions for what it means to be a ring, where you have to have a 1, a subring where you have to contain the multiplicative identity of the original ring, and then where a ring homomorphism has to take the identity to the identity. So you can see fully detailed proofs from both of these perspectives in notes that I'll link to from the lecture notes page under the Pages tab of the course website. Okay, let me give one example of this lattice isomorphism theorem just to show you how this correspondence works. So let's take R equals Z, I equals 12Z. So what is R mod I? It's isomorphic to Z mod 12Z. This is one of the examples we've already seen, where this is the usual ring of residue classes mod 12. So what are the subrings of Z that contain I? Well, the first thing to note is that when does something contain the ideal 12Z? If you have DZ, if D divides 12, then DZ is going to contain 12, so it'll contain all of 12Z. So the subrings that contain 12Z correspond exactly to the positive divisors of 12. So we have Z, 2Z, 3Z, 4Z, 6Z, 12Z. So I wanted to write this down in part just as an excuse to emphasize that you contain this ideal if you divide the number. You contain the ideal NZ if you are DZ, where D divides N. So bigger number, smaller ideal, fewer things in it. So what about subrings of Z mod 12Z? Well, we have Z mod 12Z, 2Z mod 12Z, 3Z mod 12Z, 4Z mod 12Z, 6Z mod 12Z, 12Z mod 12Z. These are all subrings of the regular ring of residue classes mod 12, Z mod 12Z. So in particular, they're subgroups. So what subgroups are these? They're all cyclic. What are they generated by? By 1, by 2, by 3, by 4, by 6, by 12. Or 0, which is the same thing in this ring. So why did I write subring slash ideals? Well, we've already seen that NZ for any N is not only a subring of Z, but it's an ideal in Z. So all of these subrings are actually ideals. And that means without checking anything, I mean, you can check from the definition, but these subrings of Z mod 12Z are going to be ideals as well.